Okay, let's dive into this. Welcome to this explainer, where we're taking a look at a foundational concept that completely shifts how we understand numbers. A lot of times when we see complex algebraic notation with those straight vertical lines and inequalities, it can feel pretty intimidating. But what if I told you that all that confusing math notation is actually just a set of physical driving directions? Today, we're focusing on exactly why mathematical intervals represent simple distance ranges and how this builds the ultimate map for all higher mathematics. To really get this, let's start with a very simple, fast-paced physical reality. Imagine you're standing exactly at 0 on a long, straight road. Now I ask you to walk 3 steps. If you walk 3 steps to your right, you land on +3, right? But what if you pivot? You walk 3 steps to your left, landing on -3. The big question is, how far are you from 0? Well, in both cases, the answer is exactly the same. You walked 3 steps. You physically covered the exact same amount of ground. And that brings us directly to our core concept. Absolute value is simply the pure physical distance of a number from 0, completely ignoring its positive or negative direction. Absolute value doesn't care which way you walked, it only cares about the physical ground you covered. Both 3 and -3 have an absolute value of 3. It's an operation obsessed entirely with distance. Let's move into section 1, the distance from 0, how the machine works. Now, textbooks usually offer a really formal definition with multiple cases that can look, frankly, frightening. But you can playfully think of absolute value as a simple little decision robot. Imagine a tiny robot inspecting every single number coming down a conveyor belt. If the number is positive or 0, it cheerfully says, "Looks good," and does absolutely nothing. If the number is negative, it simply changes it to positive. Why? Because absolute value represents distance, and you literally cannot walk -5 meters. You can walk 5 meters in a negative direction, for sure, but the actual distance you traveled is always a +5. What's really fascinating here is the clear distinction this creates. Ordinary distance, which is written with those absolute value bars, simply asks how far. It gives us a plain, positive, physical distance. Directed distance, without the bars, asks how far and in which direction. So if point A is at 2 and point B is at 7, the ordinary distance is 5. If we swap them and ask for the directed distance from B to A, we get -5, meaning 5 units to the left. We need those absolute value bars anytime we only want to know the plain, ordinary distance. Which takes us right to section 2, mapping points on lines, algebra meets geometry. This is a massive shift in how we think. By taking a blank straight line, choosing a point called the origin to be 0, and defining a unit distance of 1, a number is no longer just a loose, abstract concept. The number 5 is now a specific physical location on this coordinate line. We've essentially built a map. Fractions, negative numbers, even irrational numbers like the square root of 2, they now all have exact physical locations. We've successfully turned algebra into analytic geometry. And because our numbers are now a physical map, we can easily find the exact center between any two locations using the midpoint formula. Think of it like this. If you have a child standing at position 2 and another child standing at position 8, and you want to place a third child exactly halfway between them, you just average their positions. 2 plus 8, chop it in half, divide it by 2, and you find the exact middle spot is 5. Simple, right? Let's drastically slow things down for section 3. Intervals as distance ranges, decoding inequalities. Remember our golden rule. Absolute value represents distance. So when you see the mathematical notation, absolute value of x minus 5, it directly translates into plain English as the exact distance between x and 5. You are simply asking for the distance from an unknown spot on your map, which we're just calling x, to a fixed known position at 5. And this brilliantly illustrates the real power of this translation. When you see an inequality like absolute value of x minus a is less than or equal to c, it simply means x is at most c units away from a. Imagine a house sitting at position A. You set up an invisible dog fence that extends out c units in both directions. That unknown value x, it's just the dog, allowed to roam anywhere within that defined safe distance range. So let's actually build this on our map. If the absolute value of x minus 7 is less than or equal to 4, well, we start at our center house at 7. The dog fence extends 4 units left to 3 and 4 units right to 11. Just like that, you've created a physical interval from 3 to 11. X can be literally any number inside that range. Let's move to section 4, the one-dimensional circle, the shape hidden in the math. Let's look really closely at that number 4 from our last example. In that inequality, 4 was the maximum allowed distance from our center of 7. It dictated exactly how far left and how far right we were allowed to go. So the crucial point is right here. With a center at 7 and a strict distance boundary extending out 4 units to endpoints 3 and 11, what we have actually built is a circle. Yes, an interval on a number line is actually just a one-dimensional circle. It has a center point and a radius defining a range of allowed distances from that center. We've just used basic algebra to perfectly describe a piece of geometric space. How cool is that? This geographic thinking brings us naturally to the famous triangle inequality. It states that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Now, geometrically, this is just proving that taking a direct route from point A to point C will always be shorter than or equal to going out of your way to take a detour through point B. The direct path is always the ultimate, most efficient shortcut. Now, a quick pro tip warning for the focused learner out there regarding what we'll call the square root trap. It's a very common, very dangerous algebraic mistake to assume the square root of x squared is simply x. Actually, scratch that, it is not. If x is -3, squaring it gives 9, and the square root of 9 is +3, not -3. Therefore, the square root of x squared equals the absolute value of x. Always, always remember that absolute value. Finally, let's zoom out to section 5, the gateway to calculus, and why this matters. Here's a rapid-fire review of our 7 core map rules. We've learned absolute value is pure distance, that negatives yield the exact same distance, that it's always non-negative. We learned how to read less-than as a small distance boundary, how to build physical intervals from those inequalities, and how to measure the exact distance between two specific points or an unknown point x from a fixed point A. Every single one of these rules takes a confusing math symbol and translates it into a simple, undeniable physical truth about a map. And this is exactly how you read high-level calculus. When you eventually see a terrifying limit definition like absolute value of x minus a is less than delta, you won't panic. You'll use our translation technique to read it as the distance between x and a is less than a tiny number delta. In other words, x lives in a very, very close physical neighborhood to a. It's just driving directions on a map. Which leaves us with this final thought. We started with the simple question of taking 3 steps left or right. But by turning numbers into physical points and absolute value into a one-dimensional circle of distance, we've built the precise mathematical language required to talk about closeness. And how does the simple act of measuring distance create the entire foundation for limits, infinity, and all of calculus? Well, calculus is entirely the study of what happens when we make those distance intervals infinitely small. But to even begin to grasp infinity, you first have to know how to measure the distance between two dots. Thanks for learning with us on this explainer. I hope it gave you a whole new way to view the map.